non-Faraday electrochemical modification of catalytic activity.
Well, thank you very much for staying until the end of this meeting. I will try to compensate for this. The title of the presentation is Non-Faradaic Electrochemical Modification of Catalytic Activity, and my two co-authors are Mr. Bebelis and Mr. Neofitidis. This work was sponsored by the EEC Non-Nuclear Energy Program and by the Volkswagen Foundation and by the Hellenic Secretariat of Research and Technology. Before proceeding to describe this new catalytic effect which we have found, I will just first of all remind you a few things about solid electrolytes. Solid electrolytes are solid-state materials with a conductivity due to ionic displacement. The most well-known solid electrolyte is yttria stabilized zirconia, which is a solid solution of 8% yttrium oxide in zirconium oxide. And the development of solid electrolytes in the last 20 or 25 years has created a bridge between the area of heterogeneous catalysis and electrochemistry, and today we will see some of the new possibilities which have emerged. Now, let us consider a disk of stabilized zirconia, which is a pure oxygen ion conductor, and two porous metal films on the two sides of the disk. Then this device is called a solid electrolyte cell. There are three ways in which such a cell can be used in conjunction with heterogeneous catalysis. And these are designated by A, B, and C here. The first mode is a purely potentiometric mode. In this mode of application, one uses one of the electrolytes of the electrodes also as the catalyst for a heterogeneous catalytic reaction. And this can be used and have been used for mechanistic studies. In the second mode of operation, an external voltage is applied to the cell, and therefore oxygen ions are pumped to the catalyst surface or from the catalyst surface. And as we will see today, this can cause dramatic effects on the catalytic activity of the metal surface. The third mode of operation is the fuel cell mode of operation, which we will not discuss today. This is the reactor we used. It is made out of stabilized zirconia electrolyte, and our catalyst is placed here at the bottom of the zirconia. And there is the reference electrode is on the other side. It's probably for you, Eduardo. Okay. So here is the experimental apparatus, is the reactor cell, it's the feed system, and the analysis system. We use online gas chromatography, mass spectroscopy, and infrared spectroscopy for reactant and product analysis. This is actually one of the experimental apparatuses we used. It belongs to Mr. Bebelis. This is the mass spectrometry unit, the feed system. The reactor is in the hood. Now, before we proceed to show the results, let me show to you some of our catalyst films. This is a silver film used in this investigation. This is a top view of the porous silver film, and this is a cross-section. Here you see the stabilized zirconia electrolyte, and this is the catalyst film, and this is the gas phase. And here you can see a closer view of our silver film. In the next slide, we see a similar platinum film, which we used. This is a top view, the cross-section. Here again is the zirconia. This white area is the platinum, which the film thickness is on the order of 5 microns. This is a closer view of the platinum cross-section. So the first experiment which I will describe to you is this. We will look into the oxidation of ethylene on platinum. We have our stabilized zirconia electrolyte, our platinum catalyst, and here we have a counter electrode and a reference electrode. So we can use a galvanostat or potentiostat to apply currents and voltages to this cell. And in the next slide, we will see what happens to the catalyst when we send a small current through the cell. And what happens, as you see here, as we will see here, is really dramatic. Here we are monitoring the rate of the oxidation of ethylene on platinum to CO2 and water as a function of time. Initially, the circuit is open, there is no current going through the cell, so this here is the regular catalytic activity of platinum for the oxidation of ethylene to CO2 and water. At this point in time, you use the galvanostat to apply a current of 1 microamp to the cell, so oxygen ions are pumped to the catalyst. And this is what happens to the rate. You have a 30-fold increase in reaction rate, 3,000% increase in reaction rate. And furthermore, this is a reversible phenomenon because when you open the circuit again, the catalytic rate gradually returns to its initial steady state rate. And now if you calculate, if you compare the increase in catalytic rate with the rate of oxygen ion transfer through the electrolyte, the rate of oxygen ions that go to the catalyst, you find that the former is 74,000 times larger than the latter. That is to say, for each oxygen ion that is electrochemically pumped to the catalyst surface, 74,000 chemisorped oxygen atoms react with ethylene to form CO2 and water. And this ratio we denote by lambda, and we will see, we call this an enhancement ratio. Another thing to note in this slide is that the time constant for this effect is on the order of 2 times the Faraday constant times the total platinum catalyst surface area divided by the current which we apply. Therefore, the entire catalyst surface is responding to this change in current. And here we are plotting our steady state results. We see the effect of oxygen to ethylene ratio on the regular open circuit catalytic activity of platinum for ethylene oxidation and on the catalytic activity which you induce by polarizing the catalyst at a potential of 1 volt with respect to the reference electrode. We have proposed the acronym NEMCA for this new phenomenon. It has appeared in J-Physical Chemistry a few weeks ago. This is the acronym for non-Faradaic electrochemical modification of catalytic activity. You can see here that we have a 50-fold increase in catalytic reaction rate or in turnover frequency. So to discuss this a little further, let us define the enhancement factor lambda as the ratio of the observed increase in catalytic reaction rate divided by I over 2F, which is the rate of oxygen ion supplied to the catalyst. And also let us define the rate enhancement ratio ρ, which is the ratio of the NEMCA rate divided by the regular catalytic rate, the open circuit rate. And in this slide, this again refers to ethylene oxidation on platinum. We plot the observed increase in catalytic reaction rate as a function of the applied current. And these lines here are constant enhancement factor lines, constant lambda lines. And you see that we have observed lambda values as high as 300,000. This is to say, for each oxygen ion which is pumped to the catalyst surface, there are 300,000 chemisorped oxygen atoms which react with ethylene to form CO2 and water. And since we found all this 8 or 10 months ago, my co-workers, Mr. Veyenes, Neophytidis, and Gedekakis, have worked diligently and I would say frantically and studied 8 different catalytic reactions, and with using silver or platinum or palladium as the catalyst. And with all 8 of them, we have observed the NEMCA effect. There is not one single catalytic reaction yet in which we have found the NEMCA effect not to appear when you polarize the catalyst-solid electrolyte interface. Now, in some of these reactions here, the rate is enhanced with oxygen ions pumped to the catalyst surface with anodic currents. In other cases, the rate is enhanced with cathodic currents. And we will see such an example here. This is the methanol dehydrogenation and decomposition on silver. And this at point pi t equals 0, we apply a cathodic current, so oxygen ions are removed from the catalyst surface. And as you can see, this induces significant changes in the rates of formaldehyde production, CO production, and methane production. We will see an explanation for this later. However, the central finding of our work in this area so far has been that the important parameter for explaining the Lambda effect and for describing it is not the current, but rather the voltage, the potential of the catalyst. And this is shown in this slide, where we plot the kinetic constant of ethylene oxidation of platinum under conditions where the reaction is first order in ethylene and zero order in oxygen, as a function of the catalyst potential VWR, which is the catalyst potential in relation to the reference electrode. And what we see here is typical of what we have seen with all these 8 reactions we have studied so far, namely that over wide ranges of experimental conditions, the catalytic activity depends exponentially on the catalyst potential. And in fact, if we define a dimensionless number P from the Faraday constant times the catalyst potential over RT, we have found that we can unify all our kinetic results for different temperatures for the same reaction, of course, and same catalyst. We can combine all our results for different temperatures. Here is again the case of methanol dehydrogenation and decomposition of silver, and we plot the rate of formation of formaldehyde, carbon monoxide, and methane as a function of this parameter P. And you see that again we have again this exponential dependence. Of course, for each product you have different slope and different intercept, and of course for this this is why we also see dramatic changes in selectivity for this system as we vary the catalyst potential. Well, finally, something a little more amusing. We heard a lot about CO oxidation today. It's a famous reaction for its oscillations. What we show here is that by polarizing the catalyst-solid electrolyte interface, we can do anything we want to the oscillations. Here we have an intrinsically oscillatory state, CO oxidation of platinum. We apply a small negative current, we can stop the oscillations. Or we apply a smaller negative current, and we maintain an oscillatory state with a longer period. And when you apply anodic currents, you can dramatically enhance the frequency of the oscillations. So one can control the frequency and the amplitude of these oscillations or make them disappear. So why is all this happening? In the few remaining minutes, I will very briefly describe the explanation or one explanation for this Lambda effect. This is again our solid electrolyte, and this is the catalyst electrode, and this is the counter electrode which we use to pump oxygen ions to the catalyst, and this is the reference electrode. Now here we are under open circuit conditions. We have regular catalytic activity, and the catalyst has a certain value of its work function, which let us call by phi0. When we apply an anodic current, we force oxygen ions to go to the catalyst surface. And when negatively charged ions are in contact with the metal surface, this is well known that it causes a change, an increase in the catalyst work function. So, in fact, what we are doing when we are polarizing the catalyst solid electrolyte interface is that we are increasing the work function with anodic currents and decreasing the catalyst work function with cathodic currents. And the fact that the work function of an electrode changes when you have an overpotential at the electrolyte interface is well known to electrochemists. On the other hand, surface scientists know that when the work function of a catalyst changes, then everything changes dramatically. All the catalytic properties of the surface will change dramatically. And in fact, it is easy to show that in solid electrolyte cells of the type that we use here, the increase or the change in the catalyst work function is equal to the overpotential which develops at the catalyst-solid electrolyte interface. Therefore, one has a very convenient tool for varying the work function of metal catalysts. And since, as is known from the work of Professor Goudard many years ago, heats of absorption, of chemisorption will depend dramatically on the work function. In fact, they depend linearly on the work function of a metal surface. And since catalytic rate is reasonably expected to depend exponentially on heats of absorption and activation energies, this is why we observe experimentally in the Nemka effect the catalytic rates depend exponentially on the catalyst potential, or if you want, on the catalyst work function. Now, why there are some reactions where the rate is enhanced with an increase in the work function and others with a decrease in work function? Well, just to give you a very vague idea, let us look at the case of methanol decomposition on silver, where, as you see, with cathodic currents with decreasing work function, we have a non-Faradaic enhancement in the rate of formaldehyde formation and CO formation. And as you go to more negative potentials, the selectivity drops from 90%, selectivity to formaldehyde drops from 90% to 60%. What we can qualitatively understand this behavior by noting that as you decrease the catalyst work function, chemisorptive bonds become stronger, so methanol is more strongly held to the catalyst surface, and therefore this enhances dehydrogenation and the decomposition. So to summarize, we have seen that catalytic activity and selectivity can be varied dramatically and reversibly by the Nemka effect. Second, over wide ranges of experimental conditions, the catalytic rate depends exponentially on catalyst potential or catalyst work function phi. And we have so far measured the enhancement factor values as high as 300,000. Thank you for your attention.
I think it was the best talk anyway. We have a question from Richard.
Have you varied the platinum surface area and seen the rate very proportionally to the platinum surface area?
Yes. In fact, there was no time to discuss any of this, but what we have shown is that the time constant for these galvanostatic transients is proportional to the catalyst surface area and inversely proportional to the catalyst current. Therefore, to answer to your question, yes, the rate, the catalytic rate is proportional to the catalyst surface area, of course, and furthermore, the time constants are largely determined by the catalyst surface area. Typically in our system, our surface areas are on the order of 2,000 to 3,000 square centimeters. We have found that this is a good number because it gives us a sufficient catalytic rate to be measurable and without having mass transfer problems, because as you saw, we're using porous metal films. Therefore, if we had larger surface area, we could get into problems of external and internal mass transfer limitations.
In the platinum surface area was varied under conditions where you expected the contact area between the platinum and the electrolytes would remain constant.
Right. Right.
I'm a little bit, I think it's really nice work and it's really exciting stuff, but I'm a little bit puzzled by the work function explanation. That heats of absorption go with work function is really only a correlation. There's nothing scientifically at all to prove it. In fact, there are other such correlations that just have to go along with work function. Why could you not explain the increased reactivity by just, well, the work function is really a reflection of the state of the surface and of the chemistry of the surface chemistry may happen. The current, by supplying oxygen to the surface, you're changing the state of the surface in some way. You're changing the equilibrium concentration of its source oxygen at the surface. Is that not enough? I mean, to alter the reactivity of the surface through some sort of electron transfer effect within the surface itself. Can you comment on that?
Sure. I don't know if I made this clear, but the enhancement in the rate which you get is really dramatic. You can get rate enhancements 5 orders of magnitude higher than the rate at which you supply your oxygen. So there's no way.
I understand that part of it. I understand that.
Right. So the oxygen which you supply to the surface in the form of oxygen ions is really not enough to substantially change the coverage of oxygen on the catalyst surface directly. But indirectly, yes, because you are changing the work function of the metal. Definitely the coverage, which will be dictated primarily from the absorption from the gas phase, will in general change.
But to have work function alter surface reactivity, you ought to have charged particles partaking in the reaction. And the one thing about heterogeneous catalysis is that it's globally neutral, which is the big difference between that and electrochemistry.
Oh,
so I
no.
don't understand how changing the work function, which changes the field at the surface, is going to alter surface reactivity so much.
Oh, let me tell you, if you change the work function of the catalyst surface, then the heats of absorption will change according to the early theoretical considerations of Boudard, which have been found to be in good agreement with experiment. The change in the heats of absorption you get on the catalyst surface are roughly equal to the change in the work function. So the chem-absorptive bonds become much stronger in general when you have decreasing work function and vice versa.
But there's no, but that doesn't explain it, that just correlates it.
Did you measure the work function?
No, the work function we have measured only, we have not measured directly, and we are in the process of trying to measure it with a Kelvin probe, which we have ordered. But it is a very straightforward proof that the overpotential which you measure at the catalyst solid electrolyte interface in solid electrolyte systems expresses the change in the catalyst work function. If I understand correctly your question, you're wondering how the work function is changing on the surface. Let us agree. If
I agree that the work function will change. I don't agree that that explains the enhancement.
But if your work function will change by, say, half MeV, as it does when you polarize with 500 millivolts, then will you accept that heats of absorption will also change by half MeV?
Not necessarily, no.
How much? This is what Boudard says.
It depends
Okay.
on the density of the
It depends on several things, but order of magnitude.
Coefficients and the whole thing.
Of course it does, but okay, let's assume it will change by 0.3 eV. 0.3 eV, if the catalytic rate, which will depend exponentially in this thing, is enough to give you dramatic changes in catalytic activity.
Of that magnitude that you measured?
Sure, we have two papers which are expressing J catalysis where we have quantitative, semi-quantitative agreements between such considerations based on work function and the experimental results. We do not say this is the only possible explanation, but it is an explanation which works with all the 8 reactions which we have studied so far. We are open for other suggestions of this.
Yes, Rich. I think this is very interesting. So I know we're late and everything else, but yes. Go ahead.
We're going to roll on the beer here. Is there a way to change the potential of the plasma surface just directly, as opposed to using an ion detector to change the plasma film potential?
Can you polarize with just voltage?
No, of course, because then you just change the volta potential, the psi potential. You don't change the work function. This is an important point which has to be clarified. Don't take a platinum film and put a charge on it and expect to see the Lambda effect, because then all you're doing is you're changing the volta potential. I have a slide explaining.
Do you want to say something?
I just, my comment is, I feel a little bit of a victim of bait and switch here, because you really got my attention with your factor of 300,000. And I think that's irrelevant. because the current, the oxygen current from the surface is only necessary to maintain the potential. The
Exactly.
potential does everything.
Exactly,
So
sir.
you fooled me.
But Nick, I have to say that we have been working with these things for many years, and this thing had fooled us for many years also. It is only a year or so ago that we realized that the important parameter is the potential and not the current. And you are right, you can get lambda values of the order of 10 to the 8th if you have a sufficiently small I0. This I did not discuss. The lambda is proportional to the intrinsic catalytic rate and inversely proportional to the exchange current density of the catalyst solid electrolyte interface. It was the last slide, there was no time to discuss it. We have an approximate expression for lambda which can give you the order of magnitude of enhancement factor you should expect when looking into a new system. But you are right, you got it.
All right. Well, I'd like to thank you very much to everybody involved.